Euclid's Elements, Book 3, Proposition 15. Of lines in a circle, that through the diameter is greatest, and of the others, that nearer to the center is always greater than the more remote. So here is our situation. We have a circle, and we have one line through the diameter. We'll call this AD, and another line, and we'll call this BC. And that is going to be nearer to the center than another more remote line. We'll call this FG. So what we're going to prove is, and this is through the center. So we have a diameter. We're going to say that the diameter is greater than something that is further from it, but anything closer to the center is going to be greater than. So we're going to prove that AD is greater than BC, which is greater than FG. So the first thing we're going to do is Euclid defines distance from the center, or nearest to the center, as the distance of the perpendicular from the center to the line. So from any point we can draw a line perpendicular to another line. So let's do that. From the center, we'll call this E. We'll draw a line perpendicular to BC. And likewise, we'll draw a line. Let's make this a little different looking so our orientation can be different. And let's draw another line here to perpendicular here. So we have H and K. So from book 3, definition 5, that which is nearer to the center is going to have a shorter perpendicular than that which is further. And so this is going to mean, since it's given that this is nearer to the center than this, we know that EH is going to be less than EK. So from the greater, we can cut off a piece equal to the smaller. That's book 3, or book 1, prop 3. And so we can make, let's make this KJ, we'll make EJ, equal to EH. And at this point, J, we'll make a line this way, perpendicular, and we'll extend it until it contacts both sides. And we'll call this M and N. So now we're going to connect some points here. We're going to connect ME and NE and GE and FE. The first thing we want to point out here after this is, since this is equal to this, we know from book 3, prop 14, the previous prop, that if the perpendicular is the same to any two lines, then the lines are the same. Therefore, MN has to be equal to BC. And now we want to start proving that AD is greater than MN, which is greater than FG. And so we'll start by looking at AD and then this triangle. I'll make this triangle maybe in blue. Triangle MNE. Put me over here. So we want to look at this triangle. And in this triangle, we can see that this is equal to this because they are radii of the same circle. So all 4 of those are equal. So we'll say that AE is equal to ME, and ED is equal to NE. And ME and NE are the two sides of this triangle. And we know that any two sides taken together in any manner are greater than the third. So we know, and this is from book 1, prop 20, so the combination of ME and E has to be greater than the third side, MN. But since ME and NE are both equal to this, so we can just say that this is the same as AE ED is greater than MN. But AEED is simply AD. So AD is greater than MN. So let's hold on to that. So we've proven this line is greater than this line. And remember, this line is equal to this line, so this line is going to be greater than this line. All right, now, having proved that AD is bigger than MN, we just need to prove that MN is greater than FG. And we can do that by looking again at another triangle. So I'm going to make this triangle green. We're going to compare this blue triangle, MNE, to this green triangle, FGE. So here's our green triangle, and then here is our blue triangle. And what we can see is these also are radii of the same circle. So the two legs on the blue triangle are equal to the two legs on the green triangle. And the only difference is that the blue triangle has this larger base, or this larger angle, sorry, compared to the angle here in green. And so from book 1, proposition 24, we know that if two triangles have two legs equal to two legs, and one contains a greater angle, then it's subtended by the greater side. And so since the blue angle is bigger, it's subtended by the greater side, therefore MN has to be greater than the other base, FG. But MN is, we'll just put this right here, AD is greater than MN, MN is greater than FG, therefore MN is greater than FG, therefore we have this inequality, this equality here. Well, if AD is greater than MN, and that's greater than FG, and we remember that MN is equal to BC, we just substitute that in, and now we have AD is greater than BC, which is greater than FG, and that's exactly what we were given to prove. Therefore, of lines in a circle, that through the center is greatest, and the nearer to the center is greater than the more remote. And that's what we're given to prove, so we conclude QED.